Alright, hello everybody. I'm Omar Brito Lagunas, and today we're going to be talking about some of the coolest and least talked about parts of physics and calculus: jerk, snap, crackle, and pop. So, we probably all heard of position, velocity, and acceleration, but did you know that if we take more and more derivatives, we can uncover the deeper layers of motion? These layers are very important in designing rockets, roller coasters, and even cars. Alright, so some review. So, we start with the position function. And so if we take the first derivative of position, we get velocity. And taking the derivative of velocity, we get acceleration. So position is where you are, velocity is how fast your position changes, and acceleration is how fast your velocity changes. But we can think of them like this. If you're driving, your position is your location on the road, your velocity is your speedometer reading, and your acceleration is what you feel when you speed up or slow down. So each one is the derivative of the last with respect to time. But what happens when we take even more derivatives? This graph shows jerk, which is the next derivative after acceleration. But it also shows the previous functions, and you can see the way they interact. Alright, so jerk. So jerk is the rate at which your acceleration changes. In real life, you feel jerk every time a car stops or starts abruptly. It's that sudden lurch forward when the brakes slam or the pull back into your seat when a car punches the gas. Too much jerk can be uncomfortable, and in mechanical systems, it can cause damage over time. That's why elevators, roller coasters, and even some prosthetic limbs are carefully designed to minimize sudden jerk. Alright, so now the higher derivatives: snap, crackle, and pop. So snap is the rate of change of jerk, crackle is the rate of change of snap, pop is the rate of change of crackle. These derivatives are really discussed in the intro to physics, but they are very important in extreme environments. So snap matters when jerk itself needs to change smoothly. So an example is in a rocket launch, where forces on the rocket change very quickly. Controlling snap can prevent sudden forces that could crack the rocket. Crackle and pop become important when snap needs to be fine-tuned. So think like spacecraft, missiles, and even very high-speed maglev trains. If we don't manage these high derivatives, different systems and structures can break apart because of the stresses that are imposed with them. Alright, so what are some effects of these higher derivatives in real life? So high snap means jerk changes suddenly, causing sharp shocks and even mechanical failure. High crackle means snap itself changes rapidly. So this can make it hard for control systems to predict or adjust smoothly, like auto driving cars or cruise control. High pop causes the acceleration of the acceleration of the acceleration to change. But it sounds a little crazy, but it's very important in extreme cases like spaceflight. So it really matters. This is another graph of these different higher derivatives and how they interact with the next and the one before them. It's a little hard to understand these higher derivatives, but we can think of them in a different way other than just graphs and numbers. So snap is accelerating acceleration. So pushing down on a pedal in your car in a way that makes the acceleration increase constantly. This makes the car go faster at an accelerating rate. Jerk is zero when your foot is steady in its new accelerating point and quickly becomes negative as your car begins to gain speed. So crackle comes into play if you push down on the pedal slowly at first, then harder and harder. So this would mean that your acceleration increases at an increasing rate. You are snapping at an increasing rate. Pop would be crackling on a hill. So you are already accelerating due to being on a hill, plus you are pushing the pedal, making your acceleration increase, snapping, plus you are also gradually pushing harder and harder on the pedal, which increases the rate at which your acceleration is increasing. But even higher than snap, crackle, and pop is lock and drop, which are also informally used. So lock would be crackling on a hill that gets you steeper and steeper as you go down it. So right at the beginning, you're snapping down because you're accelerating at an increasing rate. But also you are snapping the accelerating too, means you are pushing the pedal. Drop is a little more complicated. So this would be dealing with the pedal again. So you could either, one, quickly push the pedal to a position X and let your car accelerate from there, or B, gradually push the pedal to position X so your car has more acceleration near point X than near point 0. Or C, slowly gradually push the pedal to position X. But by point C, which is in between X and 0, you are slowly gradually pushing the pedal. Then near position X, you are fastly gradually pushing the pedal. So gradually increasing your acceleration variably while you go down on a downward hill, which gets steeper as you go down it, would be dropping. This is the way I understand it, but it gets a lot more complicated the more and more higher derivatives you take. Thanks for watching.